In the vast cosmos of artificial intelligence, there exists a giant, a behemoth known as Ollama, a large language model. Born from the intricate dance of algorithms and data, it has achieved an unprecedented level of sophistication. Imagine a realm where text takes on a life of its own, where words are not just static symbols, but dynamic entities that understand context, sentiment, and nuance. This is the realm that Ollama inhabits. With its deep learning capabilities, Ollama can generate text that is indistinguishable from human writing, opening up a myriad of possibilities. From generating creative content to answering complex queries, Ollama is reshaping our interaction with the digital world. Yet, like any powerful tool, it must be wielded with care. For in the wrong hands, it could be used to spread misinformation or manipulate public opinion. So here we stand at the frontier of a brave new world, where language is no longer just a human domain. Welcome to the era of Ollama, the large language model. Remember, with great power comes great responsibility. Loop back to, in the vast cosmos of artificial intelligence.
Ollama is a lightweight framework for running open-source large language models locally. It makes it easy to get started with models like LAMM2, Code Ollama, CodeUp, Falcon, Mistral, Nexus Raven, and more language model by bundling all of the necessary resources into a single package. Ollama also optimizes setup and configuration details, including GPU usage, so you can start using your model quickly and easily. Ollama is a tool that lets you run large language models on your own computer. It supports a variety of models, including LAMM2, and makes it easy to get started by bundling all of the necessary resources into a single package. Ollama also optimizes setup and configuration, so you can start using your model quickly and easily. I have removed some of the more technical details, such as the model file and GPU usage, in order to make the text more concise and accessible to a general audience. I have also focused on the benefits of using Ollama, such as the ease of use and the support for a variety of models.
This use case demonstrates the remarkable capabilities of OpenAI's image generation technology in response to a textual prompt, resulting in a visually engaging and imaginative image of a futuristic cityscape. Here's a concise breakdown. Text prompt. The process begins with a descriptive textual prompt that outlines the desired cityscape. For example, a photorealistic image of future cityscape through digital art. Include elements like drones, towering skyscrapers, and hover cars to represent advanced.
Once we have installed Ollama, we can run the Ollama run LAMM2 command to start the model. We can then interact with the model by sending it prompts and commands. For example, we could send the model the prompt "write a poem about a cat," and it would generate a poem about a cat.
The use case of creating a future cityscape showcases the capabilities of OpenAI's image generation technology, which enables the generation of visually compelling and imaginative images based on textual prompts. Let's dive into this use case and break down the key steps and concepts involved. Text prompt. The process begins with a textual prompt. In this specific example, the prompt describes a futuristic cityscape. The prompt plays a pivotal role as it conveys the creator's vision and instructions to the AI model. It provides details about the desired elements within the image, such as drones, towering skyscrapers, and hover cars. Here's a simplified version of the prompt. Visualize a future cityscape through digital art. Include elements like drones, towering skyscrapers, and hover cars to represent advancement. The prompt serves as the creative input, guiding the AI in generating the image. Generating the cityscape. To transform this text-based prompt into a tangible image, the code utilizes OpenAI's API. It calls the OpenAI.image.create function, passing the prompt as input. The AI model then interprets the textual instructions and generates an image that represents the futuristic cityscape described in the prompt. The result is a visually striking depiction of the envisioned city, complete with the specified elements. Saving the image. Once the image is generated, the code saves it as image.png on the local system. This step ensures that the output of the AI model is preserved for future reference or use. The saved image serves as a visual representation of the futuristic cityscape created based on the text prompt. Image-to-image generation. Building on the generated cityscape image, the code explores further creative possibilities. It uses the existing cityscape image as the source and calls the OpenAI.image.create variation function. This function allows for the creation of additional images that are derived from the original input image. These variations are not mere duplicates, instead, they represent artistic interpretations or alterations of the initial image. Saving the variation. The resulting image variation, which reflects a unique artistic perspective or transformation of the original cityscape, is saved as image-to-image.png. This showcases the versatility of OpenAI's technology in generating artistic renditions or alternative versions of an existing image, offering diverse creative possibilities. The Creating a Future Cityscape use case illustrates the powerful synergy between text-based prompts and AI-driven image generation. By translating a textual vision into a visually compelling image, OpenAI's technology enables creators to explore and express their imagination. Furthermore, the ability to generate image variations from an existing image expands the creative horizon, allowing for the generation of diverse and imaginative visual content.
In this use case, the code demonstrates text-to-image generation using OpenAI's API. The process involves creating a photorealistic image based on a textual description. Here's a breakdown of the code.
Setting up OpenAI API key. The code starts by setting up the OpenAI API key, which is necessary for making requests to the API.
Text prompt. A detailed text prompt is provided, describing the desired image. In this example, it asks for an image of Tom Hanks with specific clothing and environmental details.
Generating the image. The OpenAI image create function is called with the provided prompt. It returns a response containing image data in base64 format.
Saving the image, the code extracts the image data, saves it as a JSON file with a timestamp, and stores it on the local system. Reusing the image, in the second part of the code, the saved JSON file is loaded, and the image data is extracted and saved as an image file, e.g., image.png.
Creating image variations. Another text prompt is given, asking to generate variations of the previously saved image. The code uses OpenAI image create_variation to create 3 variations of the input image. The response contains these variations.
Saving variations, the code saves the generated image variations as JSON files.
To use Ollama with RAG, we can follow the steps below. Install Ollama and Chrome app. Load the web page we want to retrieve information from. Split the web page into chunks. Embed the chunks and store them in a vector database. Initialize the RAG pipeline with the vector database and the Ollama LLM. Ask a question to the RAG pipeline. The following Python code shows how to use Ollama with RAG to answer the question.
This code will first load the web page we want to retrieve information from. Then, it will split the web page into chunks and embed them using Ollama embeddings. The embedded chunks will then be stored in a vector database. Next, the code will initialize the RAG pipeline with the vector database and the Ollama LLM. Finally, the code will ask the RAG pipeline the question, what are the various approaches to task decomposition for AI agents? The output of the code is as follows. According to the retrieved documents, the various approaches to task decomposition for AI agents include hierarchical task decomposition. This approach involves decomposing a task into a hierarchy of subtasks, which are then decomposed further into even smaller subtasks until the individual subtasks are simple enough to be solved directly. Goal decomposition. This approach involves decomposing a task into a set of goals, which are then decomposed into sub-goals until the individual sub-goals are simple enough to be achieved. Operator decomposition. This approach involves decomposing a task into a sequence of operators, which are then executed in order to achieve the desired outcome. Each of these approaches has its own advantages and disadvantages. Hierarchical task decomposition is well suited for tasks that can be naturally decomposed into a hierarchy of subtasks, such as planning a trip or building a house. Goal decomposition is well suited for tasks that can be achieved by achieving a set of goals, such as winning a game or completing a project. Operator decomposition is well suited for tasks that can be achieved by executing a sequence of steps, such as assembling a product or cooking a meal.